Okay, in this module we're going to cover work, energy, and power. And we're going to begin with work. And work is a pretty simple concept. So imagine I have some object with mass, for example, a crate on the floor or something like that. And so this would be my crate here. And I apply a force on that crate and I cause it to slide along the floor and move some distance. And it doesn't matter where the distance is, it's just that you've applied a force to something and while you're pushing on it or pulling on it, you have a motion where there is a distance. Now, one thing that makes this particular picture pretty straightforward is the fact that the force is along the distance. That is, the distance that the object is moving, there's a displacement that's in the same direction as the direction of the force. But of course, we know that you could, for example, push a crate down along with the floor, but have the force be angled at some downward angle, or you could also have like a rope attached and you could be pulling upwards and still have the block slide sideways. In that case, what we would do is we would say that the force has some component or some part that is pointing down, that's pushing the box into the floor, and then there's some part of the force that's pushing the block along the direction of the distance that's being moved, and only this part, the horizontal part, the part that lines up with the distance, only that part of the force would matter in terms of calculating the work. And so we would say that the work in this case would be equal to this horizontal part of the force. This would be the horizontal part of the force. This would be some vertical part of the force. And this arrow down here, this would be the total force. So we're pushing with some total force at a downward angle, but we can sort of separate this force into the part that's pushing sideways and the part that's pushing down. And only this horizontal part, the part that's pushing sideways, the way that the distance is moving, only that force would be part of the work. And so we would say the work is that force times the distance. And that's how we calculate work. Okay, now in our experiment, the first experiment that we're looking at, we're going to actually calculate work. And so we're going to have this track, and this is an air track where this glider sort of floats on a cushion of air, and it's constrained to only be able to move in a straight line. And I don't know if you can see it here, but there's a string here that's attached to the glider, and the string goes over a pulley, and we hang off of the pulley, we hang a weight. And so when we release it, the weight is pulled downward by gravity, and it pulls the glider along the track. So in this case, the amount of weight that we hang is going to be the force that is pulling our glider downward, or pulling our glider along the track. And notice that even though the weight is being pulled down, when you're over at the glider, there's tension in the string. The string is actually pulling the glider in the same direction that the glider is moving. And so the weight that you've hung from the pulley is going to be the force that is doing work on the glider and pulling it sideways. So in this case, we can say that the work is going to be equal to the force times the distance, or that's just going to be the weight that we hang times the distance. And so let's remind ourselves how to calculate weight. If we know this is the weight that we're interested in, if we hang some mass here, remember that the weight is equal to the mass times little g, where little g is the acceleration due to gravity, and that's that 9.81 meters per second squared. And so if I hang a 1 kilogram mass as my weight here, that would be 9.81 times 1 kilogram. That would be the weight. Now there's two things that we have to pay attention to here. We have two different things with mass. We have the mass that we've hung at the end of the string here that's providing the weight, that's pulling the string down and pulling the glider over to the right. At the same time, we have the mass of the glider. And so we want to make sure that we're clear about which mass that we're using. So in calculating the weight to provide the force that's pulling the glider, we want to use the mass that's actually hung on this end of the string. So in the first experiment, we're given, in the document, we're given some different weight values, and we have to calculate the force from that weight value. We're given different mass values. We calculate the weight from those mass values using m times g. That becomes the force that's pulling the glider, and then we multiply that force by the distance that the glider moves, and that lets us calculate the work. So that's the first task in the document, is to calculate the work that's being applied to this glider for various hanging masses. Now in the next part of the experiment, we look at kinetic energy. Kinetic energy is defined as the energy due to a body's motion. So if something is moving, it has kinetic energy. And we can calculate the amount of kinetic energy that something has by using the formula kinetic energy is equal to 1/2 the mass of the body times its speed or its velocity squared. And so we can say that 1/2 mv squared is equal to the kinetic energy. And there is a very important relationship that says that the amount of work that you do is equal to the change in kinetic energy. So that would be 1/2 mv final squared minus 1/2 mv initial squared. And so that's going to be the change in kinetic energy, because this 1/2 mv final squared would be the final kinetic energy. This 1/2 v initial squared would be the initial kinetic energy. And so if I start out with this energy being 20 joules, that's the energy unit, by the way, joules. If this is 20 joules and I end up with 40 joules, then the change in energy would be 40 joules minus 20 joules, or that would give me a net work of 20 joules, 40 minus 20. And how do we calculate the work? Well, we can calculate the work by simply using our formula force times distance. And remember, this force is just the part of the force that's parallel to the distance. So we figure out what part of the force is parallel to the distance, we multiply it by the distance, and that gives us the work. And when I pull on something, I'm going to start it moving and have it speed up, and so I'm going to be changing its speed or changing its velocity, and from that I can calculate the kinetic energy that it starts with, which is very often 0. If the thing isn't moving when it starts, the velocity is 0, so the energy is 0. And then calculate the final velocity and the final kinetic energy, and from that I can calculate this change. So let's look at a quick example. Let's say we multiply our force times our distance. So we have our force times our distance, and we calculate that that's equal to 10 joules. And again, joule is the unit for work, and it is the unit for energy. We can say that if that's the net amount of work done on my mass, then the mass is going to speed up. It's going to start moving, it's going to speed up, and its kinetic energy, that 1/2 mv squared, is going to change. And so I would say that the work, which is equal to 10 joules, is going to be equal to 1/2 the mass times the velocity squared. And so if I want to know what that final velocity is, for example, I want to figure out what that final velocity is, all I have to do is do some algebra. So if I multiply both sides by 2, I can get rid of this half. And so over here I would have 2 times the work, which is, of course, going to just be this 10 joules. I'll plug that number in. And that's going to be equal to mv squared. And then if I want to get rid of the m, I can divide both sides by m, and that will cancel the m out, and I get that the velocity or the speed squared is 2 times the work divided by the mass. So again, we want to get v by itself. So we've seen that we've taken our work-energy relationship and we have done some algebra. We can now take the square root of both sides, and that'll get rid of this square here. When you take the square root, that undoes the square, and that will leave us with our answer. The velocity works out to be 2 times the work divided by the mass. And so let's say our mass is equal to 1 kilogram. And we already said that our work was equal to 10 joules. And so we could say that the velocity would be equal to 2 times 10, which would be 20 joules, divided by 1 kilogram. Take the square root, and that would be 4.45 meters per second, because we know that's the units for speed or velocity, meters per second. So in the second experiment, what you're going to do is you're going to use the value for you're going to use that formula that we just figured out to predict what the velocity of our sliding glider should be. And the one thing that you have to be careful about when you're talking about this 1/2 mv squared, in the first experiment, the mass that we were talking about, where we were calculating the weight, that was the mass that we hung off the end of the pulley. But this is the mass of the glider. So when you calculate this kinetic energy here, you want to make sure that you're using the mass of the glider, not the mass that you hung off the weight. That would give you the wrong answer. So again, just use the mass of the glider. Now, another kind of energy, we've talked about kinetic energy. There are many, many different kinds of energy. Another important energy is the idea of potential energy. And the potential energy is defined as the energy that a body has due to its position. The energy due to position. And so we can ask, why do things have energy due to their position? Well, usually it's because you had to do work against some other force to move them to that position. And so in the handout, we gave 2 examples. So the first example that we gave was if you have a mass that's attached to a spring, and you pull on it with some force and you stretch it, you have changed its position. Its position has moved from here to here, and there's some force of this spring that's going to be pulling it back, and you're pulling it forward. And so the work that you're doing is not changing its velocity necessarily, not changing its speed, because there's this extra force here that's pulling it back. And so we can say that that work, instead of going into changing the kinetic energy, is going into giving this object potential energy. And if I let go, if I remove that force that I'm pulling with, then the spring is just going to pull the mass back, and that potential energy gets converted into the energy of motion, or kinetic energy, because it'll start moving in the backwards direction. Similarly, if I pull an object upwards, I lift an object where gravity is pulling it down, I'm doing work against the force that's pulling in the opposite direction, I can give this object potential energy, and so the work that I do is converted into potential energy, and then if I let the object go, what happens to it? It falls down, it falls back down, and that potential energy is converted into kinetic energy. So potential energy kind of lets me delay the conversion of my work into kinetic energy. But that energy is there, available to let the thing move. And so, in some sense, some people like to think of potential energy as a kind of stored energy. Now, the last part of the lab is you're going to climb some stairs, and you're going to time how long it takes you to climb the stairs, and you're also going to measure how high you climb the stairs. And so that's going to give you a force times the distance, where the force is your weight. And you can, if you have access to a bathroom scale, you can get a immediately current version of your weight, a correct version. If you don't have access to a bathroom scale, most people kind of sort of know what their weight is, so just use that. That's fine. We can get by with just using an estimate in this case. But time it takes to climb up the stairs, measure the distance. So use your force, that would be your weight, times your distance, and that will calculate your work. And incidentally, again, this work starts with a W. Weight is another word that starts with a W. So in these formulas that have W's in them, don't be confused by which one is work and which one is weight. So make sure that you know which W you're talking about. And what we're doing in this last experiment is we're actually going to calculate the power. And power has units of watts. And that's going to be equal to the work or the energy divided by the time. And so you're going to simply calculate the work in going up the stairs. You're going to use your stopwatch to time how long it takes you to go up the stairs. You'll divide the work by the time, and that will give you the power in watts. And that's the last part of the experiment. So when you have finished doing that and answered the review questions in the module document, then you should be ready to take the quiz. Good luck, and I'll see you next week.